Let us look first at the heterotic string. Okay. Now this heterotic string has, is the bosonic string on one side and the superstring on the other side. Now the origin of the gravitinos was in the Ramon sector on one side and the Neveu-Schwarz sector on the other side. Okay, but now we had two gravitinos in the type 2 string because we had two Ramon sectors. You could have Ramon in this and Neveu-Schwarz in that, or vice versa. That was the origin of the two gravitinos. But here there's only one side which is super. There's only one side in which you can have the Ramon sector. Okay, so clearly this is going to be only one gravity. We will see all this in more detail when we go back to our next round of the world sheet theory. So after we can discuss supergravity and these anomalies, we'll go back to the world sheet for the superstring and try to make contact with all this stuff. So last time it was all very formal. Now we'll try to go back to the world sheet and try to do physics with it. Okay, but already it's clear here that there cannot be more than half the supersymmetry that we had for the type 2 theories. And indeed the heterotic theory is n equals 1 supersymmetric. Okay, now with n equals 1 supersymmetry we have the option. Okay, with n equals 1 supersymmetry, so n equals 1 supersymmetry is how many? It's 16 supersymmetries. And you remember when we started discussing these supergravity theories, we did some counting. And our counting told us that the largest number of supersymmetries that you could have had and not have gravity was 16. You remember why? Because we've got massless particles, so there are only 8. 8 become 4 raising and 4 lowering. And 4 raising is exactly what you need to go from -1 to 1, because each raising operator has spin half. Because between -1 and 1 there's 2, and 2 is 4 halves. Okay, so you could have a multiplet, which is sometimes called a matter multiplet. A multiplet with this much supersymmetry that does not have gravity. But of course, as we've seen from this little counting, it has to have gauge fields. Okay, because it goes from -1 to 1. So there have to be spin 1 particles. And indeed, in 10 dimensions, with 16 supersymmetries, there is a multiplet where the fields are the gauge boson and a spinor. Now, let us count the degrees of freedom. The number of degrees of freedom in a gauge boson are 8. Okay, because it's a vector of SO8 of the little group. Okay, what about the number of degrees of freedom of chi? Well, how many? Let's take a 10-dimensional spinor, or really an 8-dimensional spinor, because we should be working in SO8. Okay, so the number of spinor components is 2 to the power 4, which is 16. Okay, but you can take the spinor and make it chiral. Okay, and get another 8 degrees of freedom from here. Okay, so basically one of these chiral spinors and this gauge field form a multiplet by itself. This multiplet is sometimes called, it's called the vector multiplet. Okay, so the n equals, okay. On the other hand, the pure n equals 1 gravity multiplet. There is a pure n equals 1 gravity multiplet. Now, the simplest multiplet of supersymmetry, n equals 1, is the vector multiplet. This is the vector multiplet where you do where, if you remember our little discussion of how you generate representations of Poincare supersymmetry, there was this other n group, which you could be in any, choose to be in any representation of SO8. If you just choose that n group to be in the unit representation of SO8, you'll generate the smallest multiplet, which is the vector multiplet. But you can do something else to that n to generate another multiplet, which is the gravity multiplet. Okay? And that gravity multiplet has exactly the following. It has, surprise, surprise, a dilaton okay. Now, when we first looked at n equals 2 supersymmetry, or when we looked at the 11-dimensional supersymmetry, as soon as we wrote down a multiple, we did some counting, and we checked that there were as many degrees of freedom as we expect from 2 points of view. We checked that there were as many bosons as fermions. That will always be true. But we also checked that there were as many degrees of freedom as expected from this oscillator counting. That check, of course, used the fact that we were doing the simplest oscillator construction, that the n representation was trivial, because otherwise you have to do a tensor product, right? That depends on what the n represents. So we don't have that check here, because this is not the simplest construction, but we do have that check here. Okay, and that check is of course a trivial one, because it is that there are 16 supercharges. It's basically the same that we did. Yeah. 16 supercharges, you break them up, 8 of them are neutral, you break them up into 4 annihilation, 4 creation, and you get 2 to the 4, it's 16 states. In this construction there's no chirality. You get 16 states, 8 of them are bosonic, 8 of them are fermionic. Okay, the number of states here are just wherever they turn out to be. But we will check that it also matches the number of fermions. But first let's do the counting.
The spin in A goes from 0 to a lot minus 1 to 1, so you're somehow breaking parity.
Which one?
In this case.
No, but you see, because a G, if you look at it under 1-2 plane, has spins minus 2 to 2. A G has minus.
How is then still n equal to 1? It's not n equal to 1.
Why not? No, you see, it's very important. I think I understand your question. You are saying that if the difference between maximum and minimum spins was more than 2, how is it n equals? This is this n business. Let's remember. Let's remember what we had. We had roughly mq is equal to the spinor representation on q. But we also had, and then we had q with q was equal to whatever, something. And then we had m with m is equal to the adjoint representation on m. You know, the usual things. Right? Now this by itself was not a Clifford algebra times something else. Okay? What we did was then we constructed a new guy, q gamma gamma q. Okay? Which had the same commutation relations between itself and m as itself and itself as m did. Okay? And then we subtracted we defined an n which was m minus this n. So that now the commutation relation minus this thing here. So that now the commutation relations of q with this object was that it was trivial. Now we had a direct product between two algebras. One was the Clifford algebra. Okay? But one was this new n. Then we had to choose any representation of this new n. And then the m was the Clebsch-Gordon of this representation. And the representations we got out of the Clifford algebra. Now the representations we get out of the Clifford algebra will always go from spins minus 1 to 1. But you're Clebsch-Gordon with something else, right? So if that something else has basically spin 1 in it, you could get spin 2. And that's what's going on. Okay? Yeah, it's really worth looking at this little paper that I recommended to you by Strategy. It's one of these basic things. You know, it's one of these things where it takes a little work because you have to get the spinor conventions right and so on. But he does it all in great detail, and it's something you'll go back to all your life whenever you're doing a detailed calculation. So it's good to look at it once because you know where to go back to. So all this is worked out in great details. Half of the paper is tables. So it's a very useful paper. Okay, great. Okay, excellent. Now let's do the counting here. So this was 1, this was 35, do I remember right? 9 into 8, no, 9 into 8 by 2. Yeah, so that's 35. And this was what? 8 into 7 by 2, so 28. So this is 36 plus 28, that's 64. Lovely, 64 is a nice number. Okay. How are we going to get what's 64? Well, 64, of course, is 8 times 8. We saw that the number of degrees of freedom in chiral spinor was 8. So the number of degrees of freedom in a vector was 8. Okay? So psi mu alpha has 64 degrees of freedom. As usual, it's separated into the Gravitini degree of freedom and the other degree of freedom. The spin 3 half guy and the spin half guy. Okay? Both of them are there. And that makes up the whole Gravitino multiplet. Okay? So the graviton multiplet. So the graviton multiplet has just the basic fields in the scalar sector, just the basic fields, basic NS fields, the dilaton, the metric, and B mu. And then it has half of the fermionic spectrum of the superstring theory. Namely, it has the one Gravitino and one whatever, the other one, the spin half guy. Remember that these two are of opposite chirality because they were born with the same chirality, and then you project one with the gamma to get the spin half guy. Okay? All good? Fine. So this is the basic content of the heterotic string, except we've forgotten something. Right. So far, what is the heterotic? So in n equals 1 supersymmetry, what could you have? The only matter multiplets are the ones we produced, because we've argued that matter multiplets are unique. Right? The only matter multiplets are the vector multiplets. And then you could have gravity. So you could have as many matter multiplets as you want. You could have gravity coupled to as many fields as you want, as many matter multiplets. But there's only one kind of matter multiplet. So you could have many flavors of that. And then you could, and then you've got the graviton. But you know, every time we add a new matter multiplet, there's a new gauge invariance. But we know in the heterotic string what our gauge invariance is. It's either E8 cross E8 or SO32. So basically, we're going to have one of these matter multiplets in the adjoint of either E8 cross E8 or SO32. Okay. Now we've got a well-defined question. Now we've got a well-defined question that we can go and give our supergravity friends. Okay? Or more like take from the supergravity friends, since they'd worked this all out before, before we suggested it. The question is, look, I'm in n equals 1 supergravity in 10 dimensions. I've got a graviton multiplet, and I've got one vector multiplet in the adjoint of some gauge group. It doesn't really matter what for the supergravity people. We'll soon see it matters. Anomaly cancellation requires particular gauge groups, but that's not something the supergravity people thought about. Okay, so from the point of view of classical supergravity, I've got a vector field in the adjoint of some gauge group, and just a vector multiplet in the adjoint of some gauge group, and I've got a graviton multiplet. What supersymmetric actions can you build? And the answer is only one. with these constraints, it's enough. Okay, and we'll write it down now. See, first let's remember let's remember the heterotic string. The heterotic string on one side was the superstring, on the other side was the bosonic string. Now in the bosonic string we took 10 directions to be the 10 of space-time and the remaining 16 directions to be whatever. That made up this lattice that gave us the gauge theory. All this you remember. Now suppose you've got your harmonic oscillators. Okay, suppose you've got your harmonic oscillators on the x part, sorry, on the 10-dimensional x part. Okay, that part is going to behave just like, it's not completely obvious because but actually it's true. It's in the zero picture it's obvious. I'm claiming that once not completely obvious in the minus half picture, in which we often tend to work, where we say that the vertex operator for a gauge boson is psi mu, for instance, or for a graviton is psi mu. But in the zero picture, the superstring has the same vertex operators for simple things in the NS sector as the bosonic string did. For instance, the vertex operator for the gauge boson is del mu x, is del alpha x mu, del x mu. For the graviton is del bar. Okay, so I'm saying if you think this through, you will come to the conclusion that if you look at the vertex operators that came from the 10 non-compact directions, that's going to behave basically the same as the NS sector in the superstring. So the net conclusion is that the fields in the NS sector are these guys and the action is essentially identical. Okay, so what we get is what we had. I'm writing it in string frame. Square root gr plus del phi the whole thing squared plus h cube h. Okay, so as far as these fields go, you just get the same as for the superstring. Okay, it just made no difference. Basically, doing zero picture calculations will show you that. Okay, but this is not the only field in the theory, of course. Okay, there are also the gauge bosons. Now, what should you expect from gauge bosons? Well, clearly you're going to get plus f mu nu plus trace f mu nu the Yang-Mills action. Clearly that's going to come about. Clearly also we'll get the same e to the power minus 2 phi because these are all NS sector fields. So the same e to the power minus 2 phi that we got in the other NS sectors carries on for the ride here. Okay, it's just like, in a way, like for the gauge bosons of, okay, it's in a way you should think of these as like being the Kaluza-Klein modes of, the Kaluza-Klein gauge fields. It's just have the same coupling constant dependence. Okay, great. Okay, now is there anything complicated at all? First, I'm going to ask you, can you imagine? So great, we've written down everything. We've written down an action that's two derivative. If I want to be fancy, I'll put 4s and so on, and minus signs. 4 and minus half. All that you look up in Wojcicki, right? That's a matter of normalization. Okay. The key question we're going to ask is, the question I'm going to ask you is the following. Can we okay, I'm not going to. I'm going to tell you something. I'm sorry. It's this, that in this action, this H is not the undeformed H. It's not dB. We have the same complication that we had at type 2A theory and type 2B theory. Okay, I'm just going to tell you what comes out, and then we'll see what it means. This H is actually H tilde, and H tilde is equal to what? Is equal to dB minus, let me put a number here for a moment. We'll talk about the number in a bit. Minus alpha omega 3. Okay, where omega 3 is the Chern-Simons form, which is ADA plus 2 by 3 A cube. So I suppose the first question I should have asked you, before writing this down, first question I should have asked you is, could we just add to this Lagrangian a Chern-Simons term? Okay, and in this case there's nothing we could add. Why is it? You see, we've got to add up forms so that they add up to 10. Good. What forms do we have in our hands? We've got H and F. Now F is a strange beast because F is something non-abelian. Okay, so that's not easy to add. You need to add it with a trace. Okay, yeah, there's basically nothing you could do. Okay, as you see, the kind of thing that you might try to do in two derivative order. But right, even higher derivative order, I wonder what you could add. Well, of course, you could add more field strength. But what kind of Chern-Simons term could you add? You know, let's say you've got one H. Now you've got to make up 7 more. What do? You can't add another H. I think it's pretty tough. Yeah. You know, in the higher supersymmetries, we had so many forms in our hands that we could play around with all of them. Okay. But now you see, so a Chern-Simons term to the action was not possible because you need a 10 form. That's a big deal. But what you can do is add to the definition of H a Chern-Simons form. Okay. Now, are you guys familiar with this in gauge theory? This Chern-Simons form? Have you seen it before? Are you familiar with its properties? Good. So then I don't have to, if anyone, I'm just going to tell you various things about it. You want, what? Yeah. If you want to know more, I'll tell you more. But if you've seen it before, we won't waste the time. What are the main properties of this object? The main property of this object is this, that under a gauge transformation, under a gauge transformation, oh, this is with a trace. So we certainly don't want gauge indices hanging around. Okay, under a gauge transformation, under which delta A is equal to the usual thing, right? So d lambda plus commutator A with lambda with the right i's and the right signs and so on. Okay, under such a gauge transformation, this delta omega turns into trace into d trace lambda f. Okay, let's see that this makes some sense. This is a 3 form, this is a 3 form, that's good. Because of the d and the 2 form. It has to be linear and lambda, that's good. What's really interesting is that it's such A, that it's so simple, and B, that it's a total derivative. It's for this reason that in 3 dimensions, the Lagrangian, which is omega 3, is not obviously gauge invariant, but is actually gauge invariant under small gauge transformations. Under small gauge transformations. Under large gauge transformations, gauge invariant when the coefficient of this is an integer in some units, as you know. Okay? This kind of thing will. Okay, fine. This is the important property of this. And the fact that it changed by d of something was what allowed you to use it as a Lagrangian in 3 dimensions. But we're not in 3 dimensions. Okay? So what's the deal here? What's the point here? The point is that under a gauge transformation, this whole thing changes by minus alpha d of f, d of lambda by h. Okay? The reason it's there, the reason it's consistent with gauge invariance, is that delta b is equal to lambda times f. Trace. It had better be, and so this is really what this is really what I should have started with, logically speaking. Turns out that B is not invariant under the normal gauge transformations. In fact, it has this transformation rule. Therefore, H changes by d of trace lambda times f, which, right, yeah, H changes by this. And therefore, this combination there should be an alpha. Now where is the alpha? Delta B, probably that's right. Let me just check that. Yeah, the delta B has the alpha. Okay. Yeah. Right. Therefore, this combination here, is invariant under the gauge field gauge transformations. Okay? So, this is the key thing to remember about. This is the only complication in this Lagrangian. The complication is that B was not invariant under the non-abelian gauge transformations. It transformed in that funny way. And that's why the field strength that appears in the Lagrangian is not just dB, but is dB minus something. What is that something? It was a bit more interesting than the other things, because it was a non-abelian thing. It was this omega 3, this Chern-Simons form. Okay.
We are assuming this, or this is true?
This comes out. This comes out. As I told you, there is a unique n equals 1 supergravity. And it had this fact.
That's why you had to add this term.
I mean, this term, you go to your supergravity friends, and they will tell you it's there. Of course, this term is not free, right? It has implications for string scattering amplitudes. So if you suspect, you can go and check, right? It means, for instance, that there is a term in which there is a 3-point function. Let's see, what would its simplest implication be? There would be a term which has 1b and 2a's. So there would be a 3-point coupling between B mu nu and 2a's. And maybe in our next round when we go back to the heterotic string, we'll check that. Okay. So of course in string theory you can check. But I'm saying you didn't even need string theory for this. Just supersymmetry made it unique. Okay, excellent. So all good? Okay, excellent. Now there's something else we want to say about this supergravity, but we can only say it once we do the next one, because it's a relationship between two things. Okay. So now let's turn to type 1 theory. Okay. Now, in type 1 theory, what are we doing? We're doing this orientifold kind of, orientation, this orbifold by orientation, identifying left with right movers. Okay? Where did we get the two gravitinos from? NS on left, Ramond on right, or Ramond on left and NS on right. But now since we're identifying these two different things, once again there's only one gravitino. So type 1 theory once again is a theory with one supersymmetry. N equals 1 supersymmetry in 10 dimensions. Okay. Now in the NS sector, because it's the same as the bosonic string, I already showed you what the implications for this of this orientation. Well, we can see it again. It's trivial. The states are alpha, or if you want, psi, depending on let's do the minus half picture. Psi minus half mu, psi tilde minus half nu on 0. These are the massless sector states. Okay, but orientation preservation basically interchanges psi and psi tilde. Orientation reversal interchanges psi and psi tilde. So what does that mean? That means that it has to be symmetric in mu and nu. Okay, symmetric in mu and nu means dilaton and graviton, no B mu nu. Okay, so in type 1 theory from the NS sector, what do we expect? We'll expect the dilaton and the B mu nu. Okay. What? Sorry, and G mu nu. Now let's remember what else type 2 theory had. Okay, what type 2 theory in addition had a scalar which we call sigma, I think. It had a 2 form which was C mu nu, and it had C alpha beta gamma delta. Okay, I had not shown you how orientation acts on these Ramond sector fields. That takes a little more doing. Okay, but I will show you when we go to our next round that what it does is throw away this guy and this guy and keep this guy. It's a simple thing, but I need to show it to you, so we won't stop it. Okay, so the field content has the same. Now this you could have guessed even if you didn't know it. Why could you have guessed it? Because we know that a graviton multiplet in 10 dimensions has this content. It has a scalar, a metric, and a 2 form. So we're going to land up with an n equals 1 multiplet. The gravity multiplet has better have been. Last time it was B mu nu, now we've got C mu nu, but as far as the gravity multiplet is concerned, it's just what it is. Okay. Now, type 1 theory also has gauge fields. Because the whole point of type 1 theory was that it is the theory of open strings. And you remember, it wasn't just any old theory of open strings. Okay, there had to be these 32 space-filling branes, the Chan pattern factors. There were 32 of them. And we had this SO 32 gauge theory. You remember that? Okay. So once again, that tells us we've got matter multiplets, same matter multiplets, right? There's f mu nu, and so we're going to get an action that's going to look pretty similar. Okay, but if we get the action in the string frame, it won't immediately look similar, because some of the fields were not NS sector fields; they were Raman sector fields. And some of the fields were not open string, closed string fields, they were open string fields. So what is the action you should expect? If we get it in string frame, e to the power minus phi, minus 2 phi, you'll get square root g times r, okay, plus you will get, right, you'll get square root g times r, plus you will get this 4 del phi squared. Okay, but now without the e to the power minus 2 phi, because it's Raman sector. Okay, so plus f3 trace f3 square. But no e to the power minus 2 phi plus some zeta, let's call it. And then of course there, oh sorry, this is open string, so it should be e to the power minus phi, because open string fields come like over the 1 over g. Okay, and then plus there is the, sorry, this was f mu nu, and plus there was the whatever we called it, the d of the c. I'm calling it f3 square with some zeta. Okay. Good. So I'm going back up here. Now, again, there is a potential complication. The potential complication is that this f3 is not f3, but it's f3 tilde. And once again, we have that f3 tilde is equal to exactly. f3 tilde is d c2 minus zeta f3. Sorry, minus zeta times omega 3. Okay. Now, this is the action. Let's see if I've missed anything. There are various numbers all over the place, which I'm not bothering to write, but I will maybe make a quick comment about them. But first, let's get the structure right. Okay. Great. So we've got. So this is. Okay, now he does this, just 1 minute. It's sort of strange. He has an e to the power minus 2 phi behind his trace f, his f3. And of course, you can field redefine things to do that, but that usually introduces the dilaton into the Bianchi identity. I wonder if that's just a typo. Let's keep going. I'm going to go with this, and if we get IS duality right, we'll declare victory. No. Maybe. I'll just go with this, and let's see how it goes. Let's see how it goes. I think maybe a typo. Okay. Okay, maybe this is a good place to say, the question of whether there's an e to, at the level of just actions, if you don't know what's coming from your vertex operators and what's not, okay, at the level of just this kind of action, it doesn't really matter very much whether there's e to the power phi or not, because you can, like for the metric, you can redefine fields. Maybe this is important, so maybe I should tell you about that. Okay. See, suppose you did the following. Suppose you take your C2 and write it as e to the power minus phi times C2, I don't want to do twiddle, so prime. Okay, now let's see what we will get. Do we want to do it? Okay, so you took C2 and wrote it this way, yes. So now what was dC2 will become what? Okay, this will become so it will become e to the power minus phi, that will go overall outside. And one term will be a minus d phi wedge C2. Okay, and the other term will become just as dC2 prime. Okay, so now if you call this plus whatever extra modification you have because of the other things, if you call this your f3 tilde prime, then you can as well work in this C2 prime variable. Okay, but the price that you've paid is that you've got this explicit C2 here. Okay, and this will complicate your Bianchi identity, right? Because your F3 will include a D. You won't hit here because that will hit the D phi. No, but you will hit here and get something from here, and you can also hit here. Okay, these are basically the same term. So you get an extra thing like D. No, but this, I'm sorry, this is what you're going to call your F prime. Okay, so this was not there. Okay, this is what you're going to call your F prime. Okay, so because you're explicitly putting the e to the power minus 2 phi outside, so you will get your df prime, basically will come from here. We'll have a term which is minus d phi wedge dc2 prime. Okay, so you, at the expense of extra complication of your Bianchi identity, you can pull the e to the power minus 2 phi out. Okay, so whether it's there or not is just a matter of field redefinition. However, it's not completely trivial because it changes your Bianchi identity. And Pulchinski is working with the normal Bianchi identity. He claims there's an e to the power minus 2 phi here. I think that's probably just a mistake. Let's check. Okay. Oh, I shouldn't have. That's precisely what I wanted to check against. Okay. So I'm sorry. So we have this, and we had the heterotic string, which maybe you just remember. It had this, but this also had an e to the power minus 2 phi. Okay, and it had this. Everything had an e to the power minus 2 phi. Same kind of terms, but everything had an e to the power minus 2 phi. Now, I've told you two things that can only be consistent if something happens. The first thing I've told you is that in n equals 1 supersymmetry with this gauge, with this gauge content, we have a unique action. But now we've written down two different actions for you. These statements can't both be true unless I can do a field redefinition to go from one to the other. Okay, and now I'm going to show you the field redefinition that does this. So let's see. Let me take this side and try to transform to the heterotic side. So let's take G1, which is the metric for type 1. This I'm going to write as e to the power minus, so let me, phi h, h for heterotic, 1 for type 1, times gh. Phi 1 is equal to minus phi h. Okay? Then this of course is f tilde, yeah, no, this is, yeah, f tilde 3 was equal to h tilde 3, and a1 mu is equal to ah. Okay? I want to claim that this, okay, so let's just perform this field reaction. So the field redefinition is doing nothing to this or this, nothing also to this f tilde 3. What? Yeah, it does it in the g's. It's true. There are square root g's and g uppers. But it does nothing to the quantities. Okay? And nothing to this quantity. But it changes these guys around. So let's just make the change. First, what happens to square root g? So square root g1 is equal to e to the power minus 5 phi h square root gh. E to the power minus 2 phi 1 is equal to e to the power 2 phi h. Okay, so first let me look at these two quantities. Okay, and here phi, the minus sign goes away in this because del phi, the whole thing square. And now we have to do the change that that came about from this conformal rescaling. So first let's get all the e to the power 5 powers, right? And then we'll worry about everything else. Okay, so as far as e to the phi goes, because we did gi is equal to e to the power minus phi h gh, ri will be e to the power plus phi h rh. Okay, so square root gi ri goes to times e to the power minus 2 phi I goes to e to the power 2 phi h, e to the power minus phi h, and then e to the power plus phi h. Okay, so e to the power minus 2 phi h square root gh rh. Phi h. All good? Okay. What about this guy? Okay. This guy, it's the same because the same g inverse. So e to the power minus 2 phi, no, not worrying about the number. There might be an extra number. But e to the power minus 2 phi g square root gi del phi I, the whole thing squared, goes to e to the power minus 2 phi h square root gh del phi h, the whole thing squared. Same because there was one G inverse.
So the first term does not produce any derivative terms in phi.
It might. That will change this effective number, but it doesn't change the scaling. Okay, let's forget about numbers for now. Okay, and then what else? And then what else? And then we want this guy. So now here we want, there's one square root G and two G inverses. Square root G produces e to the power minus 5h. Each G inverse produces an e to the power h. Each. And then there was an explicit e to the power minus phi, which becomes an e to the power plus h. Okay, so there's a 3 e to the power plus phi h's, 2 e to the power minus, and then an e to the power minus 5h. So an overall e to the power minus 2h. So square root g 1 e to the power minus phi 1 f mu nu square trace goes to e to the power minus 2 phi h square root gh trace f mu nu square. Right? And now let's see if this guy also works. Yeah, this guy also works. So Polchinski just had a mistake. Right? Because this, the square root g gives e to the power minus 5h, and there are 3 g inverses. Okay? So that gives e to the power h each of them. So this also gives you an e to the power minus 2 phi h square root g, and then this f3. In the new edition of Polchinski, is this corrected? Could you check? In
F3 tilde has e power minus 2 phi. No, it doesn't have that.
It does not have. Yeah. So he's correct. My edition is an old one. Okay. So Lubosch Mortel has pointed it out. Okay. Excellent. Excellent. Okay. So we're good. Okay. We've seen that the field redefinition changes these actions to each other. Okay. Now, something that's very important about the nature of this field redefinition is this. Okay, phi 1 is minus phi h. Phi 1 was the string coupling constant in the type 1 theory. Or more precisely, G string was e to the power phi 1. Okay, phi h, e to the power phi h was the string coupling constant in the heterotic theory. What we're saying is that the two supergravities do map to each other, but the change of variables that you need to do is that G goes to 1 by G. Now, all the caveats we had in the previous discussion about the type 2 theory, all those caveats continue to apply. Nonetheless, if one makes the assumption that this strange thing continues through to an S duality, a G goes to 1 by G duality, between not, the type 2b theory was a self-duality. The same theory, a theory at strong coupling was the same theory at weak coupling. Here the suggestion is that the type 1 theory, suppose you make the claim, that you make the guess, that the type 1 theory at weak coupling, at strong coupling, is the heterotic SO32 theory at weak coupling. Then one implication of that would be that this had to be true for supergravity. This is far from establishing it. Okay? But this would be one implication. And this is an implication even though one of the theories is strongly coupled. A, because because at low energies everything is weakly coupled, so there is an effective classical description. And B, something else that I haven't told you about, that we will come to, that there is a theorem which says that in string theory the low energy effective action is not renormalized. Even the numbers behind the low energy effective action are not renormalized by coupling constant effects. This theorem uses supersymmetry. Okay, so no matter what crazy stuff is happening up at higher energies because of strong coupling, once you go down to low energies, you know what low energy effective action you're supposed to get. Okay, so once again you might suggest, if you're bold, that actually these full string theories have this strong weak coupling duality, and again people did suggest it and were disregarded but turned out to be right. Okay, so this is the other magnificent duality in the space of 10-dimensional theories. Type 1 SO and heterotic SO32 are S dual to each other. Okay, fine.
Is type 2A related to?
Type 2A is only related to M theory. So type 2A at strong coupling is in a way the most interesting of the lot. It's not some other 10-dimensional theory, it becomes an 11-dimensional theory. Okay, so what we have now is understanding for every theory at strong coupling. You might say, well, what about the heterotic E8 theory? Well, I can't remember. Have I shown you that under T duality the heterotic E8 cross E8 and the heterotic SO32 are related? Probably not, right? Okay, so this is for our next round of world sheet. You put the heterotic E8 theory on a circle and you can relate it. So even that theory we know where it becomes a strong coupling. Okay, so all these 5 superstring theories we have good conjectures for, and actually now fantastic evidence that we understand effectively what they become at strong coupling. So each of these theories has a calculable description at strong coupling. 4 of them have another weakly coupled description. And the fifth one is the most mysterious. It's this 11-dimensional theory, which we don't know how to deal with, but we know how to work with at low energies. Okay, it's the same theory. Okay, fine. Okay, excellent. So I think that's all I wanted to say at this stage about these supergravity theories before we turn to a discussion of anomalies. Any questions or comments?
When you say type 2A at strong coupling becomes this M theory, that is just some sort of going opposite of Carl Leclerc. That's what
Exactly.
Strong,
Well, strong coupling means large G string.
yeah.
Okay, so from the type 2A point of view, it's large G string. But as you said,
Oh yeah, it's the circle size that.
that becomes large. Now, how did we know that large G string? I'm going to go through all of this in some detail, but since you've asked, how do we know that large G string means large circle? Well, there's this interesting thing about type 2A theory, that it includes, you remember that type 2A theory has Ramond-Ramond one-form gauge potential. And it has d branes that are charged under that. Since there's a one-form potential, it has 0 branes, particles. Okay? Now these particles have a mass. Like all d branes, like all open string solitons configurations, their mass is 1 by G string. You remember we saw the d branes had tension 1 by G string. Right? So there's some number, which in fact we calculated for the bosonic string. And then there's a 1 by G string. Okay? Now, when G is small, this is very heavy. But when G is large, this is light. So now we've got a bunch of light particles. What theory has these? Okay. Now there's this other magnificent thing that was understood by Witt, which was that if you take the theory of n zero brains, it's governed by 0 plus 1 dimensional gauge theory. You take the theory of n zero brains and it has a bound state at threshold. Do you know what I mean? See, suppose I take proton and an electron. Proton has mass mp, electron has mass me. I can ask you, does it have a bound state? You say maybe, but if it does, the energy of the bound state will be less than mp plus me, otherwise it will not be bound.
Yeah.
Well, the accurate statement is that it's less than or equal to, but you know, equal to, what is the chance of that happening? Well, with supersymmetry it can happen. So, there is a BPS bound that tells you that the mass of something with twice the charge of a zero brane can't be less than twice the mass of the zero brane. But it leaves over the possibility that it's equal to. Of course, so you take two zero branes at infinity, they have twice the mass of the zero. But you take these two zero branes, bring them together. There is actually a bound state. There's a wave function that is normalizable. So these things that carry zero energy. Okay? And if you take 3 zero branes, there's exactly one bound state. If you take 4 zero branes, there's exactly one bound state, and so on. It's a remarkable thing, but we control supersymmetric quantum mechanics well enough to establish such results. Okay? So now the spectrum of zero branes is not 1 by g, it's not particles with mass 1 by g, it's particles with mass 1 by g, 2 by g, 3 by g, 4 by g. And actually also minus 1 by g, minus 2 by g, because there are the anti-zero, zero branes come with both kinds of charge, positively charged or negatively charged. Okay? Now, you can ask me, suppose we assume that at strong coupling we get a classical description. What classical description has a series of particles, of light particles, of mass 1 by g, 2 by g, 3 by g, 4 by g? Kaluza-Klein theory, right?
Yeah. Yes.
Once we identify g as the effective radius.
Yes.
Okay? So the picture is that type 2a theory at strong coupling is actually an 11-dimensional theory on a circle. Okay? And this fits marvelously with our first lecture on supergravity. Because how did we get 11-dimensional? How did we get type 2a supergravity?
Yeah.
By taking 11-dimensional supergravity and putting it on a circle and doing Kaluza-Klein reduction. And now suddenly we realize that the right theory is 11-dimensional supergravity without the Kaluza-Klein reduction. Keep also the 11-dimensional nodes. Isn't it incredible? It's a beautiful thing, and there's lots of evidence all this is right. No proofs, of course. There's no proofs in this game, right? In the games of duality. No proofs, ever. But lots of evidence that it's true. It's a very beautiful story coming about. Okay. By the way, just about this duality, again, we'll have another brush through duality. But since we're seeing this for the first time, there's no reason not to say it now. How does this duality work? Well, let's look at the type 1 theory. There is one NS-NS field that's conspicuously missing. Which is that? H, or B mu nu. Now, what was the fundamental excitation that was charged under B mu nu? The fundamental string, exactly. If there had been a B mu nu, the fundamental string would have been a conserved quantity. If you had a fundamental string, it couldn't disappear. Can fundamental strings disappear in type 1 theory? Yes, they can, because type 1 theory includes open strings. You can take a closed string, it can break, become an open string, and then disappear into nothing. So the fact that there were open strings immediately goes with the fact that there shouldn't be a B mu nu. Because the gauge field that ensures string conservation should not be there, because these strings are not conserved. They can break and go into nothing. Okay? So there are no stable string-like excitations in this theory. Of course, there are little vibrating strings that do this. But you take some long string and you try to make it stable, it's not there. It break. Clear? Okay. So there are no stable string-like excitations in type 1 theory. However, there was this there was this F3 that had this 2 form, this DC2. So there was another 2 form which goes with the fact that remember type 2 theory had D1 branes, D3 branes and so on. The D3 branes are not there in this theory because we projected out the C4, but the D1 branes are there. So this is a theory with string-like excitations, not fundamental strings, but D1 branes. What is the mass of this? Yeah, okay. To get these masses right, I have to move to Einstein frame, so I won't get that straight at the moment. But okay, it's clearly becoming it's clearly very heavy at weak coupling. Okay. Now you could ask, what about on the other side? Okay. What about on the other side? What are the excitations on the other side? On the heterotic theory, there are no Ramon-Ramon fields, so no D branes. But there are fundamental strings. Why not? What is this? Is an excitation. Okay, that is light at weak coupling. S duality works by interchanging the two. Okay, the D brane, the D string of the type 1 theory becomes the fundamental string of the heterotic theory as it goes from strong to weak coupling and vice versa. Okay, this is sort of reminiscent of what we saw with type 2 theory, right? The type 2b theory, I told you that the fundamental string goes to the D1 brane. Okay, but the D3 brane remains. Here there's no D3 brane, but still you have this fundamental string going to D1 brane, though in this case not of type 2 theory, but of the heterotic theory. Okay, type 2 could have self-duality because it had both fundamental and D1 strings. Here we have a theory with either fundamental strings or another theory with D1 strings, so they can be interchanged. Okay, great, fine. Let's move on. So, any other questions or comments? This is basically all I wanted to say for our first brush with supergravity. We'll come back to this very soon when we take another trip to the world sheet. We'll look at the superstring more carefully and see if we can pull out all this physics, and then look at D branes in the superstring, look at T duality in the superstring. We'll do all that now carefully, now that we understand the physics a little bit. Okay, but for this first brush, any questions? Okay, excellent. So what I now want to tell you about before we delve back into the world sheet, okay, what I now want to tell you about is anomalies. So do you guys know what anomalies are? How familiar are you with the general topic of anomalies? Where have you read about? I mean, have you taken a course?
Madhu has given some 2 or 3 student talks on this. So that.
But you've never seen this in a quantum field theory course, for instance?
The triangle diagram,
Okay, I'll give you maybe I'll give you one lecture on anomalies. Then you should know it properly, right? Okay, fine. So let's start with. Okay, so we don't have much time today, but let me do something simple. Let's try this. Let's follow Pulchinski for this part, and just review the following. Okay, fine. Um, suppose we had okay. Let's first, what is an anomaly? As we said, the word anomaly is used for two different things. First, it's used for a symmetry, what looks like symmetry that is not really a symmetry, because when you include gauge instantons, it's not a symmetry. Also, it's used for the idea of what is under a gauge. A symmetry of a theory that becomes, whose conserved current fails to remain conserved when you turn on a background gauge field for that symmetry. Okay? While logically speaking, these two things have very different implications. There's the third thing. It's a lack of symmetry in a gauged theory. So you take some symmetry which is actually not a symmetry, and that's part of a gauge theory. That just indicates an inconsistency. So anomalies do three things. Either tells you that some gauge theory you thought that you were dealing with, that you thought was a good theory, is actually bad. B, it tells you that that a symmetry that you thought you had in your action is just not there. C, it tells you that a symmetry that you have in your action is there, but will get modified if you study this theory not as it is, but in the presence of a background gauge field that couples either to that symmetry or to something else. Okay? So that it's a symmetry that's there in some simple situation, but goes away or gets modified in a particular way when you change the situation, usually by turning on a background gauge field. Okay? These are three different usages of the word anomaly. The first is terribly serious because it tells you the theory you're dealing with is nonsense. The second is not serious, but has important phenomenological implications. Yes.
So we can read back afterwards. Can you just give known examples of these three?
Okay, excellent. So, so a known example of the first one would be to take a four-dimensional gauge theory, SUN gauge theory, with a single chiral fermion. Okay, this is perfectly consistent theory if you have Dirac fermions. Okay, but if you have just a single chiral fermion, this will be inconsistent because it has your triangle cube anomaly. Okay, so it's just the gauge theory itself would just make no sense. A known example of the second theory is QCD with massless quarks. Take QCD with massless quarks. Then classically the theory has, suppose there are NF flavors of quarks. The theory has a UNF times UNF symmetry because you can rotate the left movers and the right movers, the chiral and the antichiral quarks separately, because since there's no mass, there's no term in the Lagrangian coupling the two. Okay? Turns out that out of this SUNF times SUNF times U1 times U1, where I've broken up the UNF into SUNF times U1, both the SUNFs are fine, continue to be symmetries, but only one of the two U1s is fine. The one that rotates the two fermions in the way that would have continued to be a symmetry had there been a mass, namely rotates the left and right movers together, continues to be a symmetry. But the one that rotates the left and right movers oppositely, it's called the axial U1, and that's not a symmetry. Okay? This was where anomalies were first discovered. For this guy, the Adler-Jacques-Bell, whatever, anomaly. Okay, and this has great phenomenological implications for QCD. Okay, something of the third kind, well, that's just all over the place. For instance, if you take a theory of three, let's just take a theory of a single chiral Dirac fermion in 4 dimensions. Now this theory has a U1 symmetry classically. It has a U1 symmetry quantum mechanically, it's free. Okay? But if you take this theory and you couple it to a gauge field, a background gauge field for its U1, you will find that del mu J mu will not be 0, but will be F wedge F for this U1 background gauge field. Okay, so the third kind is all over the place, occurs very easily in free theories as well. Okay?
Just by nomenclature, is the first thing, first example that you gave, is it what is called the abelian anomaly?
No, no. All these three can be abelian or non-abelian.
No, just the nomenclature. I think this, so there's an anomaly which is called which is related to the
Are you sure?
symmetry breaking, yeah.
That's chiral anomaly.
Okay, yeah.
The second one is the chiral anomaly.
Okay.
You see, chiral symmetry is spontaneously broken because of condensation of psi bar psi. But it's also explicitly broken because of, you see, let's see. Okay, so forget working today. I'll just tell you one last story and then we can stop today. Yeah, in QCD, as you all know, psi bar psi condenses, right? You all know this. The vacuum has a condensate of psi bar psi. Okay, now this already tells you that the chiral symmetry is broken because the chiral symmetry acted differently on. It doesn't psi bar is psi, right? You know, it's like the mass term, right? Psi bar psi is what comes in the mass. So it's the thing that is charged under the chiral U1, but is uncharged under the U1 that acts equally on both sides. Okay, so the UNF that was unchiral is preserved by this thing, but classically you would think that the UNF that was chiral is spontaneously broken. Okay, therefore you would expect that you would get Goldstone modes. How many of them? Well, NF squared. In real life, of course, there are no really massless quarks, but two of the quarks are very light, the up and the down. And the pions are interpreted as the Goldstone modes of chiral symmetry breaking. But when you put the pions into multiplets, even approximately, and the third quark is also pretty light, so it's depending on how much accuracy you want, you treat 2 or 3 of the quarks as light. Okay, depending on your level of accuracy, you find that instead of having 4 and 9 Goldstone bosons, you have 3 and 8 Goldstone bosons. And the reason for that is one of the UNFs that you thought was broken was never there. The U1 in that chiral UNF was just not there. It was anomalous. Okay, so it was not a symmetry to be broken. So it doesn't result in things that you get from symmetries like Goldstone bosons. Okay, now there's a long story. There's this book called what is it called? Coleman's book. Aspects of symmetry, which has this chapter on anomalies. It's a very beautiful chapter. Of course, it's not the anomalies of type 3, the third type we were talking about just now. It was mainly the second type of anomaly, this anomaly, okay, where he's discussed in great detail the phenomenological implications of this. Okay, there's a lot of beautiful stuff there. Okay, you can read about it there if you are interested. Okay, our discussion at the moment will be in the context of the first kind of anomaly, namely looking at a theory that looks like it was sensible because it was gauged, but actually may not be. And the context is this. As you might be aware, chiral fermions, chiral matter in general, are dangerous from the point of view of anomalies, could generate anomalies. And if you look at the heterotic, the type 1 and type 2 theories, there's potential for trouble. The type 2 theory, there's potential for trouble because in the type 2 theory we have a fermions are chiral. There it turns out that the anomalies just cancel. I'll show you. There's no real anomaly. Okay? But the heterotic and type 1 theories are also potentially dangerous because they also have chiral fermions. They have only one fermion. Okay? And these heterotic and type 2 theories from traditional measures, as I will explain to you, look like they're anomalous. They're actually not, but we have to understand how. Okay, so I will tell you about this, but maybe in my next lecture on anomalies, I will give you a slightly broader view because, as you know, anomalies are being used very much to constrain low energy field theories, quite independent of this kind of thing, both in particle physics and in high energy physics and condensed matter physics. So it's good to understand it from a slightly broader point of view. Okay.
Sorry for this,
Not at all.
but there's too much confusion. So the third type you said is what is called tooth anomalies, right?
The third type is what is called Tooth anomalies, correct. Correct. You see, from a really modern point of view, the first two things are just nothing.
Yeah.
The first thing is nothing because it was a theory that didn't make sense, so we should never have looked at it.
Yeah.
Okay? I mean, it's something about the sociological attempt to build a theory. It's not about physics, right? Okay? You didn't have a theory to start with, so what are you talking about? Okay? The second thing is more interesting, but it's also nothing. Why is it nothing? You see, because the reason we thought in the first place that there was a symmetry was classical physics. Typically that's how it happens. Classically the Lagrangian has a symmetry, and quantum mechanically it turns out it doesn't. But what we've learned over the last, 50 years in some ways, but increasingly over the last 20, 25 years, is that what is classical and what is not is in the eye of the beholder. The same physics often has two different descriptions. And it often happens that on what is on one side a quantum an anomaly, in the sense that the classical physics has the anomaly and quantum mechanically it's broken, it's just a classical breaking of symmetry on the dual side. So this notion that it's a symmetry that's present classically but broken by quantum effects is again not a notion about the theory. It's something about your particular choice of description of the theory. It's invariantly all you can say is that it's just not a symmetry. Okay? So as a certain kind of physicists, I think if you went to the particle physics courses, you would still hear all these words. Okay? But a certain kind of physicist has become reluctant to call this thing an anomaly. It's just not a symmetry. However, what the third type, the thing you're calling Toft anomalies, are interesting because there is a point in parameter space, namely where you turn off all background gauge fields, where it is a symmetry. And that symmetry breaking is then controlled completely by physics. I mean, you can completely control the breaking of symmetry. So that is the most dynamically useful thing. Though the other two are also useful in attempts to build theories, for instance.